ରେକର୍ଡିଂ ଚାଲିଛି।
ଆଡ୍ କରିପାରିବ ତ ଯୋଉ ପିଲା ଆସିବ ଆଡ୍ କରିପାରିବ ତ?
ମାନେ ରେକର୍ଡିଂ ହେଲା ୟାର ସରିଲାଣି ମୁଁ ତ ଖାଲି କହିବି
ଏଇ ଦେଖ ଏଇଟା କଣ Am I audible? Am I audible, Champa?
सर्वर स्लोर से अनम्यूट कर दो म्यूट अछि के तार सबमिट बजाना
मेसेज देखिए लिखुछन देनो चंपा प्रति Nuja Chobe,
Yes, sir.
mute your microphone. Nuja. Nuja, mute your microphone and unpin yourself. Nuja, are you listening to me?
Yes, sir.
Mute your microphone. You see, microphone
should be muted. Controls components.
Do you face any problem in muting? Mute microphone बंद करो.
Yes, sir.
ये सब उड़िया पिला.
जो माइक्रोफोन सिंबल देखा जाउची सेइतरे हाथ मार दियो बंद हो जिवो. गोटे माइक्रोफोन सिंबल देखो तुम्हें मोबाइल रो ऊपर हाथ मारो माइक्रोफोन आसी जीवो देखे दबो माइक्रोफोन सिंबल
सर नहीं है बार.
नहीं है बार.
नहीं.
चंपा कैन यू हेल्प हर?
सीता पाखर नहीं ना.
Champa, am I audible? Champa, am I audible? Sambit, am I audible to you? Sambit, am I audible?
Yes, sir.
Okay, okay. Says Nuja Chobe to microphone mute करि पारुनी. ताको टिके बतेबो केमति माइक्रोफोन म्यूट करिवो.
लेफ्ट कर दिया होगी. ना अच्छा. सिटी में 6 5 है.
6 अछि बा.
अच्छी.
हां.
Food 6.
6 people 6 लगाओ.
नहीं इंक्लूडिंग आमे ना
इंक्लूडिंग आमे 5 जन जॉइन करछन.
ना ना 6 जन बा. 6 जन जॉइन करछन देखछि.
6 जन हेले एटी 7 लेखा আছে.
6 बा मु गणी देली गोटोरा हमकु छाडी कि आमे हो जे
7 हेले.
हां
7 हेले के
सेटा एनरोलमेंट ले नंबर लिख
ना संबित पटेल दीटा पड़े आछि. हे संबित दीटा करथे.
गोटे म्यूट अछि ओडा अनम्यूट अछि. तो धीरे पिक्चर देखो जी.
Okay. Nuja, now you able to mute your microphone. Okay. Okay. Now we will start our session. I request our Professor Mathematics, Professor Ashok Das, to continue his lesson today. Champa join karibo. First audible kouju ko Champa join karigalani. Problem okay. First ko am I audible to you?
नहीं दिवा तुम ऑन तो अच्छी है हेलो welcome to all learners of Indira Gandhi National Open University. Now I am going to teach about the sequence and series of functions. Then is your point-wise convergence and uniform convergence. First, sequence and series of functions. Everybody know about what is a function. Sambit, Champa, do you know what is a function?
Relation between the two sets.
Very good. Any other definition of function? Function means it is a binary relation between two sets. For example, A and B. And the domain of the binary relation is equal to first set, that is A. And each element of A corresponds to or maps to one and only one element of the set B. Then we say that F is the binary relation which is a function from A to B. Next, we are going to discuss about the sequence and series of functions first. Definition first. I have already discussed with you about the sequence and about the series. That is the sequence and series we have already discussed in the previous classes. Now we are going to discuss about the sequence and series of functions and also point-wise convergence of the series and uniform convergence. Well, first definition, let Fn be a sequence of functions. Let Fn be a sequence of functions means if n is equal to 1 to infinite, then the series is of functions is your, that is your f1, then f2, then f3, then f4, like this. First definition is your, let Fn n from 1 to infinite be a sequence of functions. It may be real or complex. The sequence of functions means when you put in place of n equal to 1, it becomes f1. Then when we put n equal to 2, then it becomes f2. Like this, f1, then f2, then f3. This is a sequence, and in each term of the sequence is a function. So this sequence is called as a sequence of functions. And each function is defined on a set E. Suppose the sequence of numbers fnx, n from 1 to infinite, converges for every x belongs to E, then one defines a new function f by fx is equal to limit fnx n tends to infinite. This is the very definition of sequence of functions. Now I am repeating you further. That is, if fn n from 1 to infinite be a sequence of functions, and these functions each that is f1 or f2 or f3 like this, each function is defined on a set capital E. Suppose the sequence of numbers fnx n from 1 to infinite converges for every x belongs to E, then one defines a new function f divided by fx is equal to limit fnx n tends to infinite. In this case, we say that the function fn converges to f or E, or Fn converges pointwise to f on E. We call the function f the limit function of the sequence Fn. This is the very definition of the limit function. That is the function Fn converges to small f on E, or it is also called as Fn converges pointwise to f on E, or they say that the limit function of the sequence Fn, that is f. Then we consider the convergence of a sequence of functions with domain prescribed in like this. That is, first we are given some examples. Let fnx is equal to nx divided by n plus x for x greater than equal to 0. We are going to discuss about this function fnx. Let fnx is equal to nx divided by n plus x for x greater than equal to 0. It is obvious that when n tends to infinite, this becomes, that is limit n tends to infinite fnx is equal to x for every x greater than equal to 0. Because when fnx is equal to nx by n plus x, divide both sides, numerator and denominator, by n. We get the numerator as nx by x, n, that is x. And the denominator, when we divide it by n, it becomes n by n, that is 1 plus x by n. When n tends to infinite, fnx becomes, that is your numerator is your x, but the denominator becomes 1 plus x by infinite, but something by infinite becomes 0. So 1 plus 0 in the denominator, that is 1. So the total result is your x by 1, which is equal to x. That is, limit n tends to infinite fnx is equal to x for every x greater than equal to 0. For any non-negative number x, for every non-negative number x, that is x greater than equal to 0, then limit of fnx n tends to infinite, that is equal to x. Secondly, there is another example. Let fnx is equal to x to the power n, where x greater than equal to 0 and less than equal to 1. Then fx, that is equal to limit n tends to infinite fnx, that is equal to 0 if x greater than equal to 0 and less than 1. That is when x is in between 0 and 1. At that time, fnx, when n tends to infinite, it becomes 0. And this fnx n tends to infinite becomes 1 if x is equal to 1. Do you follow me? Hello, Champa? Hello? Now I am
Yes,
repeating
sir.
the same one further. Define a function fnx is equal to x to the power n, where x greater than equal to 0 and less than equal to 1. Then the function fx, that is limit n tends to infinite fnx, that converges to 0 when x is greater than equal to 0 and less than 1. That is when x is greater than equal to 0 and less than 1. At that time, the value of fnx n tends to infinity, that's simply fx, it becomes 0. But when x is equal to 1, then n tends to infinite, fnx becomes 1 only. Then the third example, let fnx is equal to nx divided by 1 plus n square x. For x greater than equal to 0, then fx, that is equal to limit fnx n tends to infinite. This is equal to 0 for every x greater than equal to 0. Because it becomes, since we define fnx is equal to nx divided by 1 plus n square x, that is equal to, divide this numerator and denominator, divided by n square. Then we get numerator becomes x by n and the denominator becomes that is 1 by n square plus x. When n tends to infinite, the numerator becomes something by infinite, that is 0. But the denominator becomes, that is x plus 0. That is 0 by something, this becomes 0. So that the fnx, that is nx by 1 plus n square x, for x greater than equal to 0, then the function fx, this converges to 0, that is limiting value of fnx n tends to infinite, that becomes 0 for every x greater than equal to 0. Next, there is another example. Let fnx is equal to 1 by 1 plus nx. 1 plus 1 by nx. This and it is defined for x greater than equal to 0. Then fx is equal to limit n tends to infinite fnx. This becomes 0 when x is greater than 0. And this becomes 1 when x is equal to 0. When x is equal to 0, this becomes 1. But when x greater than 0, this limit n tends to infinite fnx is equal to fx, that value becomes 0. So from these examples, we have taken in sequence of continuous functions. The limit function is not always continuous, because in second and fourth, above converges to this in the second case, and in the fourth case, the above converges to discontinuous functions, because these have two different values. Now, one has to determine which of the properties of convergent sequence of functions. In that case, its limit function we find. Then we have seen that continuity is not a property that is preserved in pointwise convergence. This is not to say that continuity is never preserved. Actually, we have seen in first example 1, and in the third, that the limit function is in fact continuous. So it will be useful to investigate that extra condition besides pointwise convergence will guarantee the retention of the continuity by the limit function. Now we are going to discuss the continuity in the limit function. Hello, Sambit? Hello? Sambit? Hello? Hello? कौन एमती गुण गला
कौन कौन तो कौन माइल
मु किछि माने म गले एंटर मार लिए
एंटर मारन
कौन दा मारियो
हां
ना ना एमपी स्क्रीन डार्क हो गला किछ देखा गला नहीं मुझे जो
स्क्रीन डार्क हो गला
हां पूरा बंद हो गला कंप्यूटर
कहीं की
कौन के
हां
ये ऑप्शन समान 1 टू जॉइन बंद कहीं गला
कौन तो मारथिबो
ମୁଁ କିଛି ଛୁଇଁନି ବା ମୁଁ କହୁଛି ଏଡେ
छुईनी कौन
ବିଦ୍ୟାଳୟ ମୁଁ କିଛି
हां
ଛୁଇଁନି।
ओके 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 कंटिन्यू से बाहर गले को समस्त सुनी पारछी
ହ୍ୟାଲୋ ଚମ୍ପା am I audible to you? ହ୍ୟାଲୋ
Yes, sir.
ହଁ ଶୁଭୁଛି। Now we will discuss the continuity of the limit function. Let fn be continuous and limit n tends to infinite. Fnx is equal to fx. I am giving another example. Let f is to be continuous. We will need limit fy y tends to x. That is equal to fx. Since each fn is continuous, we have fnx is equal to limit y tends to x fny. Hence, for f to be continuous, we need limit y tends to x, limit fny, n tends to infinite is equal to limit fnx, n tends to infinite equal to limit n tends to that is equal to limit n tends to infinite, limit y tends to x fny. Next, I am giving another example. That is your let fnx is equal to 1 plus 1 by nx x greater than equal to 0. It is easily we can verify that's limit n tends to infinity, limit x tends to 0 plus, then fnx is equal to 1. But limit x tends to 0 plus, limit n tends to infinite, fnx is equal to 0. But both are not equal. So we see that a sequence of Riemann integrable need not converge to Riemann integrable function. But we have discussed in the previous class that's a function in what case it is Riemann integrable. Next, that is your example 3. Let fmx is equal to limit n tends to infinite cos m factorial pi x to the power 2n, where x belongs to R. Then we can find fmx is equal to 1 if m factorial x is an integer and fmx is equal to 0 otherwise. Hence, if x is irrational, fmx is equal to 0 for every m belongs to capital N. But if x is equal to p by q, where p belongs to z and q belongs to n, then cos m factorial pi x whole to the power 2n, it becomes 1 for m greater than equal to q. Hence, we have limit m tends to infinite, fmx is equal to 1 if x is a rational number, that is x belongs to q. So we have fx is equal to limit m tends to infinite and n tends to infinite, limit cos m factorial pi x to the power 2n, it becomes 1 when x is rational, and this becomes 0 when x is irrational. Means x belongs in first case, that is when this value is equal to 1, that is for x is an rational number, and it becomes 0 when x is an irrational number. But previously we know it that in this case f is not Riemann integrable. Similarly, we can show some examples. First, let fnx is equal to sin nx to the power q divided by square root of n when x belongs to R and n belongs to capital An. Then is your for all x belongs to R, fx is equal to, that is your fx is equal to limit n tends to infinite fnx, that is 0. Hence, the derivative of fx, that is f dash x, is equal to 0 for all x belongs to R. But fn dash x, that becomes square root of n cos nx, which does not converge for any value of x. So 0 is equal to f dash x, not equal to limit n tends to infinity fn dash x, that is equal to infinite. So in this example, we show that a sequence of Riemann integrals need not converge to the integral of limit function under pointwise convergence. Next is your example. Let for x greater than equal to 0, less than equal to 1, fn x is equal to n square x whole into 1 minus x square whole to the power n. Then is your n belongs to n. In this case, limit n tends to infinite. In this case, n tends to infinite. Fn x is equal to 0 for x greater than equal to 0 and less than equal to 1. But integration over 0 to 1 fn x dx is equal to n square integration over 0 to 1 x 1 minus x square to the power n dx, that is equal to n square by 2 integration over 0 to 1 t to the power n dt. That becomes n square by 2 whole into n plus 1 when this tends to infinite when n tends to infinite. So infinite is equal to limit n tends to infinite integration over 0 to 1 fn x dx is not equal to integration over 0 to 1 limit n tends to infinite fn x dx, and that equal to 0. So that these two are not equal. So in this example, we have that point-wise convergence is not enough to preserve the continuity or derivative of the integral. So to proceed further, we'll see some examples. Let fn x is equal to x by 1 plus nx when x greater than equal to 0 and less than equal to 1. It is obvious that for each value of x greater than equal to 0 and less than equal to 1, limit n tends to infinite fn x is equal to 0. So suppose choose epsilon greater than 0, we want to find n0. It belongs to capital N such that fn x minus 0 mod, that is equal to x by 1 plus nx less than epsilon. So for n greater than n0, for x is equal to 0, we can take n0 is equal to 1. For x greater than 0, the inequality, that is fn x minus 0 mod equal to x by 1 plus nx less than epsilon. This holds only if n is greater than 1 minus epsilon by x epsilon. This means that n0 depends on both epsilon and x. In fact, in this case, we cannot find an n0 which is dependent only on epsilon and independent of x. So it will satisfy the previous one. That is precisely, it becomes 1 minus epsilon by x epsilon, arbitrary, very close to infinite. In fact, supremum of 1 minus epsilon by x epsilon, x belongs to 0 and 1 closed interval. This equal to infinite, and so no such n0 can be found. But since for every delta greater than 0, supremum of 1 minus epsilon by x to the power epsilon, x belongs to closed interval of delta 1 is equal to 1 minus epsilon by delta epsilon. We can choose n0 is equal to 1 minus epsilon by delta epsilon plus 1 such that the previous one holds for n greater than n0 and for all x such that delta greater than 0 less than equal to x less than equal to 1. In this case, n0 depends only on epsilon and not on x belongs to delta 1 closed interval. One can easily guess that the possibility of existence of such an n0 would guarantee the possibility of interchange of limit in all the cases. So all these lead to the following concept. Then we go to the uniform convergence. That's all about the point-wise convergence. But then we go to the uniform convergence. Then the very definition of uniform convergence. Let Fn be a sequence of functions with domain E. We can say that Fn converges uniformly if there exists a function f with domain E, such that for every epsilon greater than 0, we can find an n0 depend on epsilon but not on x, such that fnx minus fx mod less than epsilon. For all x belongs to capital E, for all n greater than n0, so in this case we can write limit m tends to infinite, fnx is equal to fx. This converges uniformly. One can say that the uniform convergence implies point-wise convergence, that the limit function is always unique. Then there is one theorem we call that Cauchy criterion. That is, let Fn be a sequence of real or complex valued functions with domain E. Fn be a sequence of real or complex valued functions with domain E. The sequence Fn is uniformly convergent if and only if for epsilon greater than 0, we can find n0 belongs to n depending on epsilon but not on x, such that fmx minus fnx mod less than epsilon for all mn greater than n0 and all x belongs to E. For n greater than m greater than n1, hence it follows that for n greater than m, so we'll prove this, that is the fnx minus fnx mod less than epsilon. So to prove this, let for every x belongs to E, fnx is a Cauchy sequence of real or complex numbers. Hence, from the completeness, fnx converges for each x belongs to E, which proves that it is point-wise convergence. Now suppose x belongs to E, then limit n tends to infinite, fnx is equal to fx. To show that this converges uniformly, so that limit m tends to infinite, fnx minus fmx mod, that is fnx minus fx mod, this less than equal to epsilon for n greater than n0 and x belongs to E, so that n0 has been chosen independent of x, which proves that this convergence is uniform. So the above theorem gives a necessary and sufficient condition of uniform convergence of sequence of functions. That is, it proves for the uniform convergence. Then there is another theorem. Suppose that limit n tends to infinite, fnx is equal to fx, x belongs to E, and let mn equal to supremum of x belongs to E, fnx minus fx mod, then fn tends to f uniformly on E, if and only if limit n tends to infinite mn is equal to 0. Then proof the conditions implies for uniform convergence. Conversely, suppose that fn converges uniformly to f, then for epsilon greater than 0, we have one n0 belongs to n depending on epsilon but independent of x, such that fnx minus fx mod less than epsilon by 2. for n greater than n0 and for all x belongs to E. Since n0 is independent of x belongs to E, the inequality implies that Mn is equal to supremum of Fnx minus Fx mod for x belongs to E is less than equal to epsilon by 2, which is less than epsilon. For n greater than n0, this we prove that this is true, that limit n tends to infinite, Mn is equal to 0. That Fn converges to F uniformly. That is, it is the case of uniform convergence. Then we'll go to that the point-wise convergence. That is, we conclude that the point-wise convergence does not necessarily imply for a uniform convergence. Then I am giving one example. That is, Fn z is equal to 1 plus z square up to dot z to the power n minus 1. This is one GP series. 1 plus z square up to z to the power n minus 1. It becomes 1 minus z to the power n by 1 minus z. For z mod less than 1, limit n tends to infinite, Fn z is equal to 1 by 1 minus z. But supremum of Fn z minus Fz, Fn z minus Fz mod, where z mod less than 1, it becomes supremum of z to the power n by 1 minus z mod when z mod less than 1, which is non-finite, hence the convergence is not uniform. However, if for some delta greater than 0 and less than 1, z mod less than equal to 1 minus delta less than 1, then supremum of Fnz minus Fz mod less than equal to 1 minus delta to the power n by delta, which tends to 0 as n tends to infinite. Hence, the convergence is uniform for z mod is less than equal to 1 minus delta. That is, the uniform convergence of a series of functions can be defined in a same manner. Then the definition of the series of functions, that is your summation of Fnx n from 0 to infinite defined on E is said to be converged uniformly in X if the sequence of partial sums, that is Snx, which is equal to summation of Fkx k from 0 to n, converges uniformly in X belongs to E. Now we are going to give a test of uniform convergence of series of functions. Next is your another theorem for testing of uniform convergence, which is called as the Weierstrass-M test. Suppose Fn is a sequence of functions defined on E, and that Fnx mod less than equal to Mn for all x belongs to E and n belongs to n, where Mn is a sequence of positive constants. The series summation of Fnx n from 0 to infinite converges absolutely and uniformly on E if summation of Mn converges. Before going to proof, we know from Cauchy's criterion of uniform convergence, we conclude that summation of Fnx converges uniformly if and only if given epsilon greater than 0, there exists n0 belongs to n such that summation of Fkx k is equal to m plus 1 to n mod less than epsilon. That is for n greater than n0. Since summation of mn is convergent, we can find n1 belongs to n such that mk less than epsilon for k from m plus 1 to n. In this case, this arises for n greater than n1. Hence, We know that for n greater than m, which is greater than maximum of n0, n1, then modulus of summation of fkx k from m plus 1 to n less than equal to summation of k from 1 plus 1 to n mod of fkx less than equal to summation of mk k from m plus 1 to n, which is less than epsilon. Now, from comparing the first with the last one, the summation of fnx is uniformly convergent. Then we are going to test for another which used for uniform convergence, which is called as the Dedekind's test. Let the series summation of akx3, summation of anx, bnx, summation of anx into bnx, n from 0 to infinite, converges uniformly on E if these three conditions are satisfied. The one is your Snx is equal to summation of akx k from 0 to n is uniformly bounded on E. That is, there is a constant k greater than 0 such that for all x belongs to E, n belongs to n, then Snx mod less than equal to k. Secondly, summation of n from 0 to infinite bnx minus bn plus 1x mod is uniformly convergent on E. Third is bnx tends to 0 as n tends to infinite, which is uniformly convergent in x belongs to E. So using the Abel's partial summation formula to this proof, then therefore we have that these above three conditions implies or symbolizes or used for the convergence of the series summation of anx bnx n from 0 to infinite with these three conditions. Next is example 7. If the series summation of ak converges absolutely, then the series summation of ak cos kx summation of ak sin kx are also uniformly convergent on the set of real numbers or on R. Before going to prove this one, since cos kx mod less than equal to 1 and sin kx mod less than equal to 1, so that summation of ak cos kx mod less than equal to summation of ak mod. Similarly, summation of ak sin kx mod less than equal to summation of ak mod for all x belongs to real number. So, by the Weierstrass test, the series are uniformly convergent. So, in case of particular summation of sin pi x by n square, n equal to 1 to infinity, is uniformly convergent and absolutely convergent for all x belongs to the set R. Then is another example to show that the series summation of x into e to the power minus x to the power k from 1 to infinite is uniformly convergent in the closed interval of 0 to. Since we have given that fx equal to x e to the power minus x, it is, you know, it is continuous and also differentiable on the closed interval of 0 to. So its maximum and minimum occurs when f dash x is equal to 0. But differentiating this function f dash x, that is minus x e to the power minus x plus e to the power minus x, this vanishes only at x is equal to 1. Now since f0 is equal to 0 and f1 equal to e to the power minus 1 and f2 equal to 2 e to the power minus 2, so it follows that f0 less than f2 and less than f1, hence maximum of the value f occurs at 1 and it is e to the power minus 1. So fx mod to the power k is less than equal to e to the power minus k, where x belongs to the closed interval of 0 to. Since summation of e to the power minus k is convergent, so by the Weierstrass test, that x e to the power minus x whole to the power k is uniformly convergent on the closed interval of 0 to. Next is your, that is, this is for the uniform convergence. Then there is another example, so that we have to show that the series sine pi x by n to the power alpha, where n equal to 1 to infinite, is uniformly and absolutely convergent for alpha greater than 1. But if alpha greater than 0 and less than equal to 1, then it is uniformly convergent. In first case, it is uniformly and absolutely convergent. And the second one, it is uniformly convergent in every open interval, sorry, in every closed interval C and D, where 2k pi less than C less than D and less than 2 whole into k plus 1 pi, but not in any interval containing the points 2k pi A belongs to J. I am repeating this one. That is, will show that the series summation of sin nx by n to the power alpha, where n from 1 to infinite is uniformly and absolute convergent for alpha greater than 1. But if alpha greater than 0 and less than equal to 1, then it is uniformly convergent in every interval, that is closed interval of C and D, where 2k pi less than C less than D less than 2 whole into k plus 1 pi, but not in any interval containing the points, that is 2k pi, where k belongs to Z. Then we are going to solve this one. That is, if alpha greater than 1, then summation of n from 1 to infinite 1 by n to the power alpha is convergent. Hence, from the Weierstrass test, the series is absolutely and uniformly convergent. If alpha is greater than 0 and less than equal to 1, we use the Dedekind's test. That is, we know that modulus of summation of k from 1 to n sin kx is less than equal to 1 by sin x by 2 mod. If x not equal to 2k pi, if the closed interval of CD is as prescribed, then it follows that modulus of summation of sin kx k from 1 to n less than equal to maximum of 1 by sin c by 2 mod or 1 by sin d by 2 mod. Since 1 by n to the power alpha, where n alpha greater than 0 is monotonically decreasing to 0, it follows that the condition of Dedekind's test are satisfied. Hence, the series converges uniformly in the on the closed interval of C and D. If x is equal to 2k pi plus minus pi by 4n, then using the fact that sine theta greater than equal to 2 theta by pi, where theta greater than equal to 0 less than equal to pi by 2, we have alpha greater than 0 and less than equal to 1, summation of sine rx by r to the power alpha, where r is equal to n plus 1 to 2n mod is equal to summation of 1 by r to the power alpha sine pi r by 4n r from n plus 1 to 2n mod is greater than equal to summation of 2 by pi into r pi by 4n into r 1 by r to the power alpha, where r varies from 1 n plus 1 to 2n is equal to 1 by 2n summation of 1 by r to the power alpha minus 1, where r equal to n plus 1 to 2n is greater than equal to 1 by 2n into summation of 1, where r equal to n plus 1 to 2n, that gives equal to n by 2n, which finally gives 1 by 2. So that this necessary condition for uniform convergence of the series is not satisfied here. Hence, We verified that this example for the that is summation of n equal to 1 to infinity sin nx by n to the power alpha. Hello? Hello, Champa? Hello? Hello? Borsarani? Hello?
Yes, sir. Yes, sir.
What today the
Yes.
block 6 was, that is a sequence and series of functions. Then was point-wise convergence and uniform convergence. There is a little thing about the uniform convergence of continuity. So there is a condition that we have already seen that continuity is not necessarily transferred to the limit function under point-wise convergence. So we'll discuss the uniform convergence preserves the continuity. So from the theorem, let Fn be a sequence of continuous functions on E, which is a subset of the set of complex numbers, which converging uniformly to F on E, then F is continuous on E. Actually, this is the time. So your time is over. Now I am going to end your class now. Thank you.
Yes, sir. Thank you.